So we ended section 4.2 on page 4 of your handout on Monday. And what we learned on Monday, okay, was the exact value of the sine and cosine function for quadrantal angles, right, which are integer multiples of 90 degrees or pi over 2 radians. And then we learned about the periodicity of the sine and cosine functions, right? They have a period of 2 pi radians or 360 degrees. And then we learned about the even and odd properties of the sine and cosine function, right? Cosine is an even function, and sine function is an odd function, right? And so you can take advantage of those properties and evaluate sine and cosine at negative angles. And then we reviewed angles that are multiple of 30 degrees and 45 degrees, right? 30 degrees, 45 degrees, and 60 degrees. Using geometry, we can find the exact value of the sine and cosine function, right, for those three angles. Okay. So on the top of page 5, okay, we're going to evaluate sine and cosine function at select angles, and we'll be taking advantage of the unit circle, okay, posted on the next page. And most of you, when I asked if you're familiar with this, you told me that you were. So first we're going to evaluate the exact value of the sine of 2 pi over 3 radians. Okay? And so remember, whenever we're given an angle that has pi in it, we assume it's in radians unless we're told differently. Okay? So here on the unit circle, okay, now remember all the points on the unit circle, right? The x coordinate is equal to the cosine of the angle, and the y coordinate is equal to the sine of the angle. Okay. So here's 0 degrees or 0 radians, right, on the positive x-axis. As we go around in a counterclockwise direction, right, you find the angle of 2 pi over 3 radians, which is the same as 120 degrees, right? You know how to convert from radians to degrees and degrees to radians. And the y coordinate for that point, right, that would be p of t in this example, right? The y coordinate for that point is square root of 3 over 2. So the sine of 2 pi over 3 radians, its numerical value is square root of 3 over 2. Next, we have the cosine of 5 pi over 6 radians. So again, right, here's 0 degrees and 0 radians on the positive x-axis. And as we go around in a counterclockwise direction, we find the angle 5 pi over 6 radians, which is the same as 150 degrees. And that point on the unit circle, right, this is the x coordinate, this is the y coordinate. And so the cosine of 5 pi over 6 radians is equal to the x coordinate for that point on the unit circle, which is minus square root of 3 over 2. Next, we have the sine of 7 pi over 4 radians. So again, right, here's 0 degrees, 0 radians. We go around in a counterclockwise direction, right, we get to the angle 7 pi over 4 radians, which is the same as 315 degrees. Here's the point on the unit circle at, for that angle, right? Here's the x coordinate, here's the y coordinate. The sine is equal to the y coordinate, which is minus square root of 2 over 2. And so you notice that all the x coordinates and the y coordinates, right, is kind of the same, right? You have the same set of numbers making up the x coordinates and y coordinates, right? Some are positive, some are negative. And that all follows from what we talked about on Monday, right? These angles, 30 degrees, 45 degrees, and 60 degrees, right? We know the exact value of sine and cosine for those angles. And these other angles, right, they have their numerical values, right, are either plus or minus 1/2, plus or minus square root of 2 over 2, or plus or minus square root of 3 over 2. Okay? So it's like the same set of numbers. See, it's either going to be positive or negative. Okay? All right. So next we have the cosine of minus pi over 3. And cosine's an even function, so we can write this as the cosine of plus pi over 3, right? Cosine is an even function. And the cosine of pi over 3, right, go around in a counterclockwise direction. Here's the angle cosine pi over 3, which is the same as 60 degrees. And we noted on Monday, right, cosine of pi over 3 is equal to 1/2. And then the cosine of minus 300 degrees. Again, cosine's an even function. So the cosine of minus 300 degrees is the same as the cosine of plus 300 degrees. So you go around the circle, you come to the angle cosine 300 degrees. Come to the angle cosine 300 degrees. And cosine of 300 degrees is the x coordinate for this point, which is equal to 1/2. And then lastly, we have the sine of 225 degrees. So as you go around the circle in the counterclockwise direction, you come to the angle of 225 degrees. The sine is equal to the y coordinate at this point, which is minus square root of 2 over 2. So your homework assignment, right, which I didn't remind you the due date, but it's tomorrow night, right? If you remember saying that, right? It's fairly short, but it's a lot of this. Okay. What's the sine and cosine for various angles? Okay. All right. So any questions on that, ladies and gentlemen? Okay. All right. So on the next page, or on the previous page, on page 5, right, it says find all values of t in the interval from 0 to 2 pi, right? So that's one trip around the unit circle, right, counterclockwise direction. That satisfy the given equation. The sine of the angle t is equal to square root of 2 over 2. Now the interval is from 0 to 2 pi, so the implication is t has to be in radians. So we got to find all the angles t in radians between 0 and 2 pi that satisfy that equation. Well, remember, sine is the y coordinate, okay? For all these points on the unit circle. So sine of what angles is equal to square root of 2 over 2, okay? Well, as you go around looking at the y coordinates, right, you see this point, right, has a y coordinate square root of 2 over 2, and that corresponds to the angle pi over 4 radians. So sine pi over 4 radians is equal to square root of 2 over 2. And as you go around the unit circle, okay, you come to this point on the unit circle and you see that its y coordinate is equal to square root of 2 over 2. And so the sine of the angle 3 pi over 4 radians is equal to square root of 2 over 2. Okay. And there are no other points, right, on the unit circle that have a y coordinate of plus square root of 2 over 2. So these are the pi over 4 and 3 pi over 4 are the only two angles on the unit circle where the sine of those angles is equal to square root of 2 over 2. So the solution to our equation is t is equal to pi over 4 and t is equal to 3 pi over 4. Any questions on that? All right. And the next one, we have the cosine of t is equal to minus the square root of 3 over 2. So again, right, starting here at the angle 0, as we go around the unit circle, we look for an x coordinate of minus square root of 3 over 2. And we get over here to this point on the unit circle, it has an x coordinate of minus root 3 over 2, and that corresponds to the angle 5 pi over 6. So cosine of the angle 5 pi over 6 radians is equal to minus root 3 over 2. And as we continue around the unit circle, down here, right, this point has an x coordinate of minus root 3 over 2, and it corresponds to angle 7 pi over 6. So the cosine of the angle 7 pi over 6 is also minus root 3 over 2. And there are no other points on the unit circle that have a x coordinate of minus square root of 3 over 2. So the two angles on the unit circle, right, from 0 to 2 pi, that satisfy this equation are t equals 5 pi over 6 and t equals 7 pi over 6. Okay. Any questions on that, ladies and gentlemen? So now you have everything you need to successfully complete the WebAssign homework. Alright, so in this section, 4.3, we talk about the graphs of the sine function and cosine function. Now, the role of x and y is different in this section from the previous section with the unit circle. Remember, x and y, right, in this section are the x coordinate and the y coordinate, right, for a point on the unit circle, right? You know, a unit circle is a circle of radius 1 and has its center at the origin. Okay. In this section, okay, x is the input to an equation and y is the output. Okay, so these are not technically as I think about this, their role is similar, okay, but it's expanded. Okay, so x is still, well, no, these are, excuse me, I take that back. Okay, x, the role of x and y is different. X is the input, y is the output to an equation. X is the input, is an input, is the angle that goes into the sine function, and y is the numerical value that comes out of it. Okay, so we're going to graph the function f of x equals sine x. Right? This is its equation. Remember, y values and function values are the same thing. So y is equal to sine x. X is the input angle. Y is the output value. Okay, and in graphing a function, right, an equation, right, one technique, this is how I learned, this is actually how I learned in high school, right, you select some values of x, you calculate the corresponding values of y, and then you form the ordered pairs, and then you plot the points and play connect the dots. So, my values of x, I took, right, the input angles. I took the quadrantal angles from the unit circle. Right? Remember, quadrantal angles are multiples of pi over 2 or 90 degrees, right? So I wrote the quadrantal angles in both radians and degrees. And so the sine from the unit circle, the sine of 0 radians is 0. The sine of pi over 2 radians is 1. The sine of pi radians is 0. The sine of 3 pi over 2 radians is -1, and the sine of 2 pi radians, right, is 0. All this we know, right, we showed in section 4.2. Now we form the ordered pairs, right, the x and y coordinates for points in the coordinate plane. So the first point 0, 0, the second one's pi over 2, 1, then pi 0, then 3 pi over 2, -1, and then 2 pi over 0. Now we plot those points. And so here's the point 0, 0. In the coordinate plane, right here. The point pi over 2, 1 is right here, right? Here's pi over 2 on the x-axis, right? Here's 1 on the y-axis. So here's the point pi over 2, 1. Right? Here's the origin, 0, 0. Then here's the point pi 0. Then here's the point 3 pi over 2, -1. And then here's the point 2 pi, 0. Okay. So we plot those 5 points, and then we play connect the dots. And when we connect the dots, right, we have this smooth curve from the origin, right? This is the tallest point in the graph of the sine function, right? So we go from origin up to here, and cross the x-axis here, and come down here, which is the lowest point in the graph of the sine function, and then come up here. Now we talked about section 4.2 that the sine function and the cosine function have a period of 2 pi radians or 360 degrees. So that means that the graph of the sine function, graph of sine x, is going to repeat itself every 2 pi radians, or 360 degrees. So this is the graph for one period from 0 to 2 pi radians. And so if you notice, you pick up the graph and move it over 2 pi radians, you get the same pattern all over again. Okay, starting here, it comes up. Here's the top of the graph, crosses down here. Here's the bottom of the graph, and then comes back to the x-axis here. So from 2 pi to 4 pi, this is another period in the graph of the sine function. Now you notice that down here I have the word cycle. Cycle is another word for period. Okay? So when you hear about the graph of a trig function for one cycle, it means for one period. Okay? And so because the sine function is periodic, right, it repeats its values every 2 pi radians. You see, if we pick up the graph and move it to the left 2 pi radians, we get the same graph from minus 2 pi to 0 radians. It's another cycle. Okay. So the sine function, which is defined for all real numbers, right? It's defined for the sine of 1 million radians, and it's defined for the sine of minus 12 million radians. Okay. It's defined for all real numbers. Its graph, because it's periodic, repeats itself every 2 pi radians, right? The graph just keeps repeating itself over and over and over, forever to the right and to the left, every 2 radians, for 360 degrees. Okay. So down below, right, I have some information on the sine function, right? Its domain is all real numbers. You can put in any value for x, and sine x is defined. The range of the sine function, right, is bounded, right? The minimum value of the sine function is -1, and the maximum value of the sine function is +1, right? So all the y coordinates in the graph of y equals sine x are between -1 and +1. Okay. The y-intercept, where it crosses the the y-axis, is the origin here, 0, 0. Okay. And as already noted, the period is 2 pi radians, or 360 degrees. Okay. Where it crosses the x-axis, right, are at integer multiples of the number pi. So you can see it crosses the x-axis at -2 pi, -1 pi, 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, and so forth. Okay. And we noted already that the sine function is an odd function, and odd functions have origin symmetry. And so if you turn the graph upside down, right, you get the same graph, okay, for the sine function. So that's what the graph of the sine function looks like. Okay. Down below is the corresponding graph for the cosine function, right? For f of x equals cosine x. So again, right, x is the input angle in radians, and y is the numerical value of the cosine function for that input angle. Now, like I did up above, in graphing the cosine function, right, I selected some values of x, calculated the corresponding values of y, right, and then you form the ordered pairs. So again, I used the quadrantal angles, right, multiples of pi over 2, but I wrote out my values of x for 2 cycles instead of just 1 cycle in this case, right? So for the first cycle, the angles go from 0 to pi over 2 radians, and then for the second cycle, the angles go from 2 pi over radians to 4 pi. Okay. So I wrote everything out for 2 cycles, and those are all quadrantal angles, right? Multiples And you can see that the numerical values for cosine x, right, they repeat themselves. So from 0 to 2 pi, right, these are the numerical values for the cosine function. 1, 0, minus 1, 0, 1. And then from 2 pi to 4 pi, right, those numerical values repeat themselves. 1, 0, minus 1, 0, 1. Okay. And that's what we mean by periodicity, right? The cosine function repeats its values every 2 pi radians, or 360 degrees. So our first order pair is the point 0, 1, which is this point right here on the y-axis. So that's the y-intercept. Our second point is pi over 2, 0, which is right here. Our third point is pi minus 1, which is right here. Our fourth point is 3 pi over 2, 0, which is right here. And our fifth point is 2 pi over 1, which is up here. This is 0, 1. And so for one cycle or one period, right, this is what the graph of the cosine function looks like, right? It starts here on the y-axis, comes down, crosses here on the x-axis, reaches its lowest point right here at pi, comes up, crosses the x-axis again, and then ends at its highest point again at 2 pi 1. Okay? And so you can see from, here's the origin. So here's the graph from 0 to 2 pi, and you can see the graph from 2 pi to 4 pi looks exactly the same as it does from 0 to 2 pi. Right? That's due to its periodicity, the cosine function repeating its values. And you can notice from minus 2 pi to x equals 0, the graph looks exactly the same as from 0 to 2 pi. And that's all due to periodicity. Okay. The cosine function repeating its values. So, as with the sine function, the domain is all real numbers. The range is from minus 1 to 1. Okay. Those are the y values. Okay. So the minimum y value is minus 1. The maximum y value is plus 1. Right? Those are the y coordinates. Y-intercepted, right, crosses the y-axis at the point 0, 1. And it has a period, right, of 2 pi radians or 360 degrees. And because the cosine function is an even function, right, the graph has y-axis symmetry. So the graph to the right of the y-axis, right, is a mirror reflection of the graph to the left of the y-axis. Okay. And where it crosses, graph crosses the x-axis is at odd integer multiples of pi over 2 radians. Okay. And you can see that, right? It crosses at minus 3 pi over 2, minus 1 pi over 2, plus pi over 2, 3 pi over 2, 5 pi over 2, and so on. Okay. So that's what the graph of the cosine and sine functions look like. Okay. So if you flip over your handout, at the top of page 2, we have a transformation of the sine function. This is a transformation of y equals sine x, right? You remember transformations of functions that we studied back in chapter 2. So here we replace x with x plus pi over 2. Remember, pi over 2 radians is 90 degrees. So when you replace x with x plus pi over 2, okay, it shifts the graph to the left, pi over 2 radians, right? And so here's the graph of y equals sine x for one period, right? It starts at the origin. And now that entire graph gets shifted to the left, pi over 2 radians. Okay. Well, when we shift the entire graph to the left, pi over 2 radians, we end up with the graph of cosine x, y equals cosine x. So it turns out, right, that the graph of the transformed graph, right, sine function, y equals sine of x plus pi over 2, is the graph of y equals cosine x. Okay. So the difference between the sine graph of sine function and cosine function, right, is what is called a phase shift. A phase shift of pi over 2 radians. Okay. And a phase shift is just another word for a horizontal shift, right? Or say transformation, shifting the graph either to the left or to the right. Okay. Down below we have the graph of y equals the cosine of x minus pi over 2. Okay. So this is a transformation of the graph of y equals cosine x, okay, where we replace x with x minus pi over 2. So here's the graph, right? Remember the graph of y equals cosine x crosses the y-axis at y equals 1. So here's the graph of cosine x. And when we replace x with x minus pi over 2, right, it shifts the graph right pi over 2 radians, or units, I should say, either way. Okay. And so when we shift the graph to the right, pi over 2 units, okay, we get the graph of y equals cosine x minus pi over 2, which is the same graph as that of y equals sine x. So the graph of y equals cosine of x minus pi over 2, right, is the same as the graph of y equals sine x. Okay. So cosine x, so up above here, right, the sine of x plus pi over 2 is equal to the cosine of x, okay? And down below here, okay, cosine of x minus pi over 2 is equal to sine x. We can make those conclusions, okay, based on the graphs. Okay. So pi over 2, the amount of the horizontal shift, right, is actually called a phase shift. It's the amount of the horizontal shift. Okay. Any questions on that? All right. So top of page 3, we're going to talk about transformations, right? Transformations, right, in the graphs of the sine function and cosine function. And so the transformations are going to be of the form y equals a times the sine of bx plus c, and y equals a times the cosine of bx plus c. Okay. So we studied transformations of functions back in chapter 2. Okay. And so we're just continuing that discussion here, but we're applying it to the sine graph of the sine function and graph of the cosine function. Okay. Now, so a, b, and c are real numbers. from our study of transformations of functions, right? Remember, we have like y equals f of x, and if we multiply the right-hand side, the function f of x on the right-hand side, by a constant c, a real number c, right? That either caused a vertical stretch in the graph of f of x, or it caused a compression in the graph of f of x, right? Remember, if c was greater than 1, it was a stretch. If c was between 0 and 1, it was a compression. And so a here, right, acts like c, right? It determines the amount of the vertical stretch or the vertical compression in the graph of the sine function or the cosine function. So the amplitude, what we call the amplitude, is the absolute value of a, and it is just, strictly speaking, right, the amount of the vertical stretch or compression. Okay. The b in the argument here, remember, bx plus c inside parentheses is called the argument. The b inside the parentheses, right, determines the period, how often the graph repeats itself. And so to find the period, right, we take the number 2 pi and we divide it by b. So that gives us the period from page 1. That gives us the length of one cycle in the graph of the transformed sine function or cosine function. Okay. And the phase shift is determined by the absolute value of c divided by b, and that is the amount. Remember, phase shift is another word for horizontal shift. So that is the role of A, B, and C, okay, in the transformation in the graph of the sine function or cosine function. Okay. And so I need to take attendance, so we'll stop right here and we'll do graphs